What's going on, everyone? This is Jay Patel. In this video, we will be deriving the equations for the backpropagation in neural network. If you have seen my previous videos, then you would know that we came up with these equations for the backpropagation algorithm, but we didn't derive these terms, del cost by del w and del cost by del p. So in this video, that's what we are going to derive. And if you haven't seen my videos on the neural network, then make sure to check those out because I think I have provided the best possible explanation along with the mathematical details behind it and the intuition behind it. So make sure to check that out. You can find its link in the description box or by clicking at the I button in the upper right corner. Also, whatever I'm going to implement here, you can find that in the form of PDF from the description box below. You can download that PDF and have that for your reference, and you will also find the complete derivative process in that, so you can refer that as well after you complete with this video. And in this video, I do assume that you know the basics of derivatives and how to calculate the derivatives. If you do not, then I will also provide a link in the description box where you can learn the basics of the derivatives that we require. And if you haven't subscribed to this channel, then this is your chance to subscribe right now and also hit the bell icon so that you get notified. And this video is going to be a bit long one, but a really informative one. So make sure to stick till the end and let's get started with this video. We will be deriving the equations for the backpropagations for the neural network having two hidden layers. So let's look at the details of this neural network. We will be passing input x and out and getting output y. A1 and A2 are going to be hidden layers and A3 is going to be the predicting output layer. Then there are going to be W1, W2 and W3, which are going to be our weights. If you have seen my previous video, then you might have seen that I have used the notation W superscript 2 and A superscript 2, but that I'm representing as A2 for simplicity in this video. Let's say the number of neurons in the input layer is N0 and that of a first hidden layer is N1 and N2 and N3 respectively. Now we will look at the shapes of all these A's and W's, and it is going to be a very important one because while you are implementing this in Python, if you make a mistake in the shapes, then you will get an error which you won't be able to solve if you don't know about the shapes of these. So the shape of W1 is going to be N1 comma N0. So the shape of W is nothing but the number of neurons in the next layer and the number of neurons in the previous layer. Similarly, W2 is going to be N2 comma N1 and W3 is going to be this. And similarly, the shape of B1, B2 and B3 are going to be N1 comma 1, N2 comma 1 and N3 comma 1 respectively. If M is equal to the number of observations or the number of data points we have in our data set, then the shape of the input data is going to be N0 comma M, where N0 are the number of features in the data and M is the number of observations. Thus the shape of A1 is going to be N1 comma N, A2 is going to be this, A3 is going to be this, and Y is going to be N3 comma M, which is going to be the same as our predicting output A3. Now about the activation functions that we are going to use. In the first layer, we will be using F1 as our activation function. In the next layer, we will be using F2. And these F1 and F2 are going to be either ReLU or tanh activation functions. We can use any of these two, so we will keep it as F1 and F2 respectively. For the output layer, we can either use sigmoid or we can either use softmax activation function. But here, in this video, I'm going to use sigmoid activation function in the output neuron. In the next video, we will derive the equations for the softmax activation function. And as we are using sigmoid activation function, N3 is going to be just 1 here, but I will keep it as N3 for now. And about the Z can be given by W multiplied by A of the previous layer and adding B there. And as we are using sigmoid, our cost function is given by this logistic regression cost function or binary cross entropy cost function, and thus the loss or the error for one single observation, for ith observation, is going to be given by this. So we got our details, so now let's derive the equations. Let us first start by calculating del L by del W3. Here L represents the error for one observation. Then we will combine the error for all the M observations to get the del cost by del W3. And the loss or L is given by this equation, where this AI is A3 and A3 is given by sigmoid of Z3 and Z3 is given by this equation. And our equation of the sigmoid is given by this. To calculate this, you will see that the L depends on the A3 and A3 depends on Z3 and Z3 depends on the W3. So we can use the chain rule in derivative to calculate del L by del W3, which will be del L by del A3 multiplied by del A3 by del Z3 multiplied by del Z3 by del W3. We will find these individual terms. Let's start with del L by del A3, which we can find by taking the differentiation of this equation. Also note that this del represents the partial derivative, which means that only a will be considered as a variable while y will be considered as a constant. So it comes out to be y minus y upon a3 minus of 1 minus of y upon derivative of log of 1 minus of a, which is 1 minus of a3, and again the derivative of this 1 minus of a3, which is going to be minus 1. So it will be minus y upon, and once we simplify this we get minus y. This and this is going to be cancelled, so this comes out to be a3 minus of y upon a3 multiplied by 1 minus of a3. So this is our del L by del a3. Now for del a3 by del z3, we will need to take the derivative of this sigmoid function. So we can write the sigmoid function in the form of 1 plus of e power minus z3 power minus 1. So its derivative will come out to be minus 1 outside, and 1 plus of e power minus z3 power minus 2, and then the derivative of 1 plus of e power minus z3, which will be minus of e power of minus z3. So this will come out to be e power of minus z3 upon 1 plus of e power of minus z3 whole square. Also 1 upon 1 plus of e power of minus z3 is nothing but a3. So this can also be written as a3 square multiplied by e power of minus z3. And if you write e power of minus z3 in terms of a3, it will come out to be 1 minus of a3 upon a3. This and this will be cancelled and we will get a3 1 minus of a3. Thus our del a3 by del z3 is equal to a3 1 minus of a3. Now we are left with this term, so our del z3 by del w3 will be the derivative of this equation with respect to w3, so it will just come out to be a2. Now we have all these three terms, let us just multiply them to get our del L by del w3. So it will be multiplying this term, then this term, and then a2. This and this will be cancelled, so we will have a3 minus y multiplied by a2 as our final equation. So this is our equation. So this is for just one observation. Now for m number of observation, we will be having del cost by del w3 instead of del L, and this we can just represent in the form of matrix. So it will be capital A3, capital Y, and capital A2. Sorry, this is A2. And we will also have 1 by m here, because if you remember, then in the equation of cost function we also had 1 by m and the summation here. So this summation is already included while we do the matrix multiplication of these two. Now we didn't consider the dimensions of these. If you see, the dimension of this a3 and y are both n3 comma m, and this is n2 comma m for a2. So we cannot multiply these two, so we will need to take the transpose of it, and once we take the transpose we will get the final dimension as n3 comma n2. And if you see, the dimension of del cost by del w3 should be the dimension of w3, because we are going to subtract this term from w3, and we know that the dimension of w3 was nothing but n3 comma n2. So this we can finally write as our equation for del cost by del w3. Similarly, we can find del L by del P3 and then combine it to get del cost by del P3. So this will be again del L by del A3 multiplied by del A3 by del Z3, and here del Z3 by del B3. But we already calculated this term, which was given by A3 minus of y, so we will just compute it, A3 minus of y, and this will come out to be just 1, because if you see here, if you take the differentiation of this term with respect to b3, this will be 0 because it is considered as a constant, and this will be 1. So del L by del b3 would be just a3 minus of y. Now we can also write this multiplication in the form of del L by del z3, and for simplicity we can represent it as dz3. So this will be easier to represent in the other equations as well. So we can just represent the del L by del b3 with dz3. Now this was only for the one observation, and when we have m number of observation, then del cos by del b3 is going to be 1 upon m dz3. Also note one thing here, the dimension of dz3 is n3 comma m, but the dimension of b3 is just the n3 comma 1. So we will need to take the column wise summation of this dz3 term, and it also makes this sense here because in our cost we already had 1 upon m and the summation term there. So for this summation we need to take the column wise sum for these. So we can write the del cos by del b3 as comma 1. Now this 1 represents the column wise summation, and from the column wise summation I mean that this column will be summed with this column and so on. Now we got both of these terms, so we will move to the next layer and we will calculate the del L by del W2. Now to move from L to W2, we will need to go from L to A3, then to Z3, then Z3 to A2, then A2 to Z2, and then we will reach W2. So to do that, we will implement the chain rule in this way. So here I have taken A3, A3 depends on Z3, Z3 depends on A2, A2 depends on Z2, and so on Z2 to W2. We already calculated these two, which we called as dZ3, so we will just keep it that way. And the derivative of del Z3 by del A2 will come out to be del W3, because our Z3 is given by W3 A2 plus of B3. So derivative of this equation with respect to A2 is going to be just giving W3. And now for the derivative of A2 by of Z2, if you remember, the A2 was given by F2 Z2. So we can just write it as a F2 dash Z2. And here the dash represents the derivative of this function. Similarly, the derivative of Z2 with respect to A2 will just give us A1, small a1. So del L by del W2 comes by multiplying these four terms, and we can get the cost by considering all the observations. Then it will be 1 upon m multiplication of these terms, but we didn't consider the dimensions into picture, so let's consider that as well. The dimension of dz3 is going to be 9 n3 comma of m. This is going to be n3 comma n2. This is going to be the same as the dimension of z2, which was n2 comma m, and this will be n1 comma m. And the resultant dimension that we are looking for is that of w2, which should be n2 comma of n1. So we can get this by taking the w3 transpose first and then multiplying it with dz3. So this 2 is going to be n2 comma n3 multiplying with n3 comma m. So the resultant is going to be n2 comma m, and this is also n2 comma m, this is also n2 comma n. So we can take the element wise multiplication with the f2 dash z2. So this entire thing is going to be n2 comma m. Then we can just multiply it with a1 transpose, and this will be our final equation for del cost by del w2. And here from the element wise multiplication, I mean that this 1 will be multiplied with this 2 will be multiplied with this 3 will be this 4, and so on. Now this can be written in the form of dz2 because this is the multiplication of these four terms, which is nothing but del L by del Z2. So we can write it as a dz2. Thus our del L by del W2, sorry, this is cost, and cost here as well, is going to be 1 upon m dz2 multiplied by A1 transpose. And now for the del cost by del B3, these four terms are going to remain the same, just we will be having del z2 by del b2, which will again be just 1. So it will be nothing but 1 upon m, and similarly sum that we took previously of d z2 and 1 again represents the column wise sum. So this will be our del cost by del b2, not del b3. Okay, so now it's time to move another layer backward and calculate del L by del W1. And again, to go from L1 to W1, it's going to take a long chain here. And you already know some of things, so I will just start it with del L by del Z2. So here I have started directly with Z2, then Z2 to A1, A1 to Z1, Z1 to W1. We already calculated that, which we wrote as dz2 in the previous slide. And again, this will be nothing but the derivative of z2 with respect to a1, which will be given by just this w2. So this is w2. This will be the derivative of the activation function f1 with respect to z1, and this will be x because the z1 is equal to w1 x plus b1. So we take the derivative with respect to w1, it is just going to be x. Again, if we take all the observations and also consider the dimensions, then we can finally write it as a w2 transpose dz2 element wise multiplication with f1 dash multiplied by x transpose. So this will be our equation for del cos by del w1, and we can write this term as a dz1, and we can write this del cos by del w1 as 1 upon m dz1 multiplied by x transpose. And for del cos by del b1, it will be 1 upon m summation dz1 comma 1, just as previously. So here we had only two hidden layers. If we had multiple number of hidden layers, then we can just continue repeating this process, only this dz term are going to change in every other layer. Here we had dz1, in the previous slide we had dz2, and the dz2 was given by this equation, while this dz1 is given by this equation, and both these forms are exactly the same, only these numbers change. So no matter how many layers we add in the hidden layers, we just need to change these numbers and we can continue repeating our steps. So let's summarize everything now. So we derived all these equations, and at the end these equations look something like this. We can directly implement this in the Python, which will be very easy once we know all these. Also note, I have written dw3 here, which is nothing but del cost by del w3. So in short, I have written it as dw3 because while programming this is much easier variable to deal with. Also, we didn't see what as our f1 and f2 are going to be. So let's say if our function f of z is a 10h function, we use a 10h function, then the 10h function is given by this equation. So its derivative, if you do it by yourself, then you will get to know that its derivative is 1 minus of the same thing square. So this is nothing but a, so it can be written as 1 minus of a square. So if we are having del if we are taking it as a f2, then it will be 1 minus of a2 square. Similarly for f1. But if we are using a ReLU activation function, which is given by x for x greater than 0, then its derivative will come out to be 1 and 0 respectively. So we can directly compute this value if we are using ReLU function, or this value if we are using 10h function. And finally, all these equations will be passed to these equations where our parameters are going to be updated, and this entire thing is going to be running in a for loop where our model will be completely trained. I know this was a big video, but it was kind of a very important one if you see the mathematics behind it. And in the next video, we will be deriving these equations if we are using the softmax function in the output layer, or if we are doing multi-class classification. And don't worry, the next video is going to be a short one. We are not going to repeat the things that we already know, but we are just going to look at things that we haven't seen before. So next video is going to be short, and after that we will be implementing the entire thing in Python from scratch. We will be implementing multi-class classification neural network with multiple hidden layers, and we will be also implementing the binary classification, and we will also see what effects it takes if we change the number of hidden layers, if we take more hidden layers or less hidden layers. So make sure to watch all those videos, continue follow along with the series, and I see you in the next video.